This last topic here is covering the worst kind of battery possible. If you have a chance, if you have the opportunity to use any other kind of battery, do that. This kind of battery is it's, it's a pretty sad little battery, but it does work. And there are some very, very specific unique situations where concentration cells actually are useful, but they are few and far between. But it's still an interesting thing to look at, an interesting phenomenon, because you might notice that when you look at the Nernst equation, what the Nernst equation implies is that a cell could be created that has the same substance as both electrodes. So you could have an electrochemical cell where the standard cell potential for your voltaic cell is 0. But because log of Q is something other than 0, you have some disproportionate concentrations of things involved in the reaction, you can actually end up with a voltage across the cell, even though you have the exact same materials on one side of the cell versus the other. This is just one of the interesting side effects of electrochemical reactions. So as long as there is a concentration difference between the two sides, you will have a non-standard cell potential that is something other than 0. In a concentration cell like this one, where you have nickel 2 plus, one side has 1 molar nickel 2 plus, and the other side only has a millimolar nickel 2 plus, the reaction will actually proceed until both sides are at essentially 1/2 molar. And then at that point, the cell is dead. But even when the reaction is going, you can see here, the voltage isn't even 1/10 of a volt. So it's not terribly strong, but I mean, it's something. It is something. So let's look at an example here. This is written in the style of question similar to what's in the book. This particular way of writing how the cell is working or is laid out shows reactants, products for one side of the cell, and then reactants and products for the other side of the other half reaction in the cell. So this half reaction here is the oxidation. This is the anode. And then even though it's the exact same half cell, this is the cathode, because we have zinc 2 plus going to zinc. So that's just a little preface here for reading these types of this notation. So we have 1/2 cell, reactants going to products. Double line here means, okay, now this is the other half cell, reactants to products. So this is our cathode. So the question is asking, what is the cell potential of the concentration cell described by this? So what would be the non-standard cell potential? So if you remember the Nernst equation, it looks something like this. Where we have the standard cell potential minus 0.0592 volts divided by n log Q. Standard cell potential, super easy, 0. So the non-standard cell potential is equal to 0 volts minus 0.0592 volts divided by n. If you look at the reaction here, you don't even have to go back to those half reactions on the table to figure out how many electrons are being transferred. You have zinc going to zinc 2 plus. That's a difference of 2 electrons. 2 electrons are being transferred. And so n is 2. And then the log of products over reactants. So if we look at the way that this is written here, this is going to be our only product, because the product over here is a solid. It's not going to show up. So we have 0.1, It's not going to be raised to anything because we wouldn't need to multiply these by any values. Our reaction, if we were actually going to write the balanced equation, it would be zinc solid plus zinc 2 plus goes to zinc solid plus zinc 2 plus. It looks kind of ridiculous, but that is the balanced chemical equation. There's no need to have any extra coefficients or anything. So that is our one product. Our one reactant is the zinc 2 plus on the other side here, which is 0.5. And so if we do the math, 0.1 divided by 0.5, take the log base 10 of that value, which is a negative 0.6989, so on and so forth. We're going to take that value, multiply it by 0.0592, divide that by 2, and then take the negative of that because we have the negative here, and that tells us that the non-standard cell potential for our little concentration cell here is, let's see, that would be positive 0.02. Oh, and I feel bad for it, so I'll round it up to 1 here. It's actually 206, but I'll just give it 21 volts. Not the largest voltage, but still, it works. That would be a spontaneous reaction. The cell would operate until they both reached 0.3 molar zinc 2 plus, and then the reaction would stop. All right, I hope that made sense. I think there's a question or two in the homework over concentration cells, so I wanted to be sure to get those in there. And I also wanted to be sure that you to show you this notation so you knew how to read that type of notation. Just real briefly here at the end of the chapter, I just want to talk over some different kinds of batteries, some batteries that you will have surely come across in your everyday life. I'm not going to read through every single point here on these. I just want to give a brief summary of some of these. Lead storage batteries, or lead acid batteries, as they're often called, in some ways are really awesome batteries, and in some ways are really terrible batteries. They're really awesome for their purpose. They are great because they are really hardy. They can, you can leave them out there out in the winter, and winter is really hard on batteries. Really cold temperatures are really tough on batteries, but these can withstand it most of the time. Eventually the battery gets old enough that the winter will kill it, but they're pretty tough. They have a decent cell voltage, a little over 2 volts, and they're easily rechargeable. So all those things make them very, very handy for using in things like cars. What makes them not so awesome is that, my gosh, are they heavy. They literally have lead in them, hence the lead acid batteries. And then the other part of that, the acid part, that's not too fun either. They have about 30% sulfuric acid, which is really nasty stuff. So they have their positives and their negatives. But there's a very good reason that we don't walk around with a backpack full of lead acid batteries to power our cell phones. We have much better options. Nickel metal hydride batteries are one type of battery that is often used for kind of the simple type of rechargeables, the cheaper kind of rechargeables. In these types of batteries, you have potassium hydroxide as the electrolyte, which was the salt bridge in the voltaic cells that we looked at, which is something that you would not want to get on yourself. So if you accidentally bust open a battery, even if it's not a rechargeable, any kind of battery, don't touch the liquid that comes out of those. They're pretty nasty liquids in there most of the time. The thing that's nice about these is that they have, number one, they're rechargeable, but they have a relatively long life. They're relatively light compared to other types of batteries, and especially because they're environmentally friendly as compared to things like nickel-cadmium batteries. NiCad batteries, in addition, have lower energy density, but NiCad batteries are kind of the older style rechargeable batteries. And the cadmium in those is not very good for the environment. It's a heavy metal, it's a toxic metal. So when those batteries go out into the landfill, it's not a good thing. The nickel metal hydrides aren't, they're not fertilizer or anything, but they're much better than the nickel and the cadmium. Lithium ion batteries, on the other hand, are the gold standard when it comes to rechargeable batteries. They are actually relatively new in the grand scheme of things in terms of power. I can remember when I was a kid, and my dad had a laptop where I'm pretty sure the battery on that thing weighed like 20 pounds. Like, it was just this giant, huge thing of a battery. And it was just a pain to carry that thing around. Nowadays, there are still some laptops, especially if they have removable batteries, that will use non-lithium ion batteries. Will use maybe a nickel or a metal hydride or something like that battery. But most laptops and tablets and cell phones especially use lithium ion batteries. The reason being, number one, again, they are rechargeable. They have relatively long lives, but especially because they are very light. Lithium batteries, because lithium is the smallest metal on the periodic table, it is very low density. You can get a lot of lithium for not much mass, as compared to something like nickel and cadmium, just giant atoms compared to lithium. And so you get a lot of bang for your buck, essentially, with lithium. You can get as much amperage, as much power in a gram of lithium as you would get in, I don't know, like 100 or so grams of the nickel-cadmium stuff. It is very, very energy dense. It's also more environmentally friendly than those heavier metals. And so, and it also has a very high cell voltage as well. So not only can you fit a lot of lithium into a smaller area, it's less, doesn't weigh as much, it's friendlier to the environment, and for each lithium you put in there, you actually get more power per lithium than you get per nickel or per cadmium from these other types of batteries. So it is in pretty much every way a better battery than those older technologies, which is why essentially everything now uses lithium-ion batteries. But there are still ways we could make them better. Real briefly here, electrolysis. This is a method that some people use to try and get reactions to occur that would not occur spontaneously otherwise. So, for example, if you want to make some hydrogen gas, super easy to do that, actually. Just hook water up to a battery, which sounds like a weird thing to say, but it's true. You take a 9-volt battery, hook some wires up to the posts. Again, don't try this at home necessarily. It's not something that 9-volt batteries aren't going to shock you enough to really hurt you badly, but I would prefer you to not play with batteries at all without knowing what you're doing very well. But anyway, you can take a battery, like a 9-volt battery, and hook wires up to the posts on that and stick those wires into water, and it will actually start to electrolysis will begin in the water. You'll have oxygen and hydrogen bubbles forming at the 2 posts that you stick in there, the 2 wires connected to those posts, because the cell voltage is giving enough energy to the water to break apart. That reaction is not spontaneous on its own, but if you give it a push, if you give it that bit of voltage, it will actually cause the reaction to happen spontaneously. And the same thing is true for electroplating. If you take a piece of, I don't know, something you're going to put on your car, or something like you want to get some really fancy rims for your car. If you want to get that electroplated, what you would do is you would take that piece of metal and you would dunk it into a solution that had something like chrome. In this case, it's showing silver, but you could do the same thing with chrome. So you would have some chrome ions in solution. Now, normally, the chrome wouldn't just plate out onto a piece of metal, but if you put a voltage on it, if you make the metal attractive to it, essentially, you give it a push to plate out onto that piece of metal, you can essentially force that metal that would otherwise stay in solution to coat the piece of metal that you're electroplating. And so this is how electroplating works, is you can take a metal like silver, and then using a high voltage source, it doesn't even really have to be all that high voltage, just a higher than 0 voltage source, you can cause the silver to plate out onto some other object, which is a pretty handy thing to do sometimes. So that will be it for this chapter. I hope you found it interesting. Please be working on the homework as soon as possible, and I will talk to you all about this the next time we get together.